welcome back to another tutorial. Today we are going to recreate Rapid Fire Map 10. This is a simple arcade game wherein you control a green spaceship as you bob and weave through incoming red boxes. Your goal is to demolish these obstacles, and as you increase your score, so does the velocity of these cubes. The game ends once the ship collides with any of the squares. This game has a pretty basic yet solid concept, making it perfect to make a video about recreating it step by step. So, without further ado, let us begin with the tutorial. Before we start coding, let us first talk about all the models and custom script blocks we'll be using for this game. Firstly, we have the player ship. You can design yours however you'd like, though the shape would be important later on. I made mine share some resemblance from the original game with the triangular shape and a green color. Then, we have a red box. Keep in mind that the bottom layer should be white, as this will be useful for indicating a box has been hit if it ever collides with a bullet. Speaking of which, this is a green bullet that would shoot out from the ship. We also have a particle that would come out from the thrusters. Notice how there are 4 faces, each of which has a different color. Essentially, we'll be applying some rotation whenever we spawn this block to effectively have 4 different particles for the price of 1. Finally, we have a score indicator that pops up whenever a player destroys a box. Make sure that all 3 of these objects are affected by physics, as this helps us with properly positioning them later. For our script blocks, we have a vector lerp located inside Fancade by Sonac, for which you can find in the block section in the build tab. Then, we also have a block size 2D by Martin Magny. What this block does is, given a camera distance, it outputs an area of how much is visible within the screen in terms of blocks. Now that we got that out of the way, let's start with the project. Bring out a script block to act as a container for all of our code. The first section of the game is the initialization process, aka what happens at the start of the game. Let's assign our player ship to a variable, set the origin point to be far away from the script block, and make sure to have the Y position be at 0.5 as we'll be using this vector to position our ship. Next, let's show our player, set its position to where O is, and update the player's current and goal position. Then, let's set up the camera so that we could actually see our ship. It's fairly straightforward. Set the origin point as the camera position, then the camera rotation should be 90 degrees in the x-axis to have a top-down view, and set the distance to around 48. We'll also use that rotation for our light to eliminate the shadows. When we press play, we can now see the player located at the middle. However, what if we want to move it to the bottom? Not to worry, all we need to do is to add an offset. Now all seems well, except it isn't. If we rotate our screen to landscape, notice how the screen has been cut off. So what do we do now? Let's say we have 2 areas, one representing the camera view and the other representing the actual device. If we rotate the device, it will obviously obscure the further parts of the camera. All we simply have to do is to also rotate that camera. Let's convert this to a make rotation block, and we'll be checking if the screen width is greater than its height. If it is, then that means the player is in landscape mode. However, we can't directly plug this here as these are 2 different data types. Although, there is a workaround. A boolean can be treated as a number that is either 0 for false or 1 for true. If we subtract these 2 values and inspect it, and for now let's put in placeholder values, it'll be positive if the first value is greater than the other and negative or 0 if not. Now, I'll just quickly add some stuff here, and when we test this, we get 1 if the first value is greater and 0 if not. Basically, what happens is after we get our difference between the 2 numbers, we check for the minimum value between the result and 1. If it's greater than, then chances are it would probably be 1 or greater, so doing this clamps that value to 1. Then, we check for the maximum value between the result and 0. If it remained unaffected from the first bit, then that probably means it has a value of 0 or less, and doing this clamps that value to 0. But we're not yet done. If the difference between the 2 given values is less than 1, then we'll end up with a decimal. All we have to do is connect it to a ceiling block. What this does is round the value up. So even if it has any decimal value, this block will round it up to the next whole number. And that fixes our problem. Finally, let's attach this to the Y value of the rotation. Now, our camera follows suit even if we change their orientation. It's time to implement the controls. The logic behind it is quite simple. Whenever the player touches the screen, we store their touch position to a variable. Then, we compare the offset between that touch position and its previous value and apply it to the ship to update its position. Let's place a touch sensor with its mode set to touching, and take the screen coordinates and convert them into a vector position via a screen to world and a line v plane. Now, we can theoretically add another touch sensor set to begins to get that previous touch position that we'll use to compare and get the offset, but what we can do is attach an if condition that checks a boolean. If it's false, which it would be by default, then we set it to true and update the tap old variable, which would act as the old value of our touch position. I'll also add another touch sensor set to ends to reset that variable back to false. After that if statement, we'll update the player goal based on the offset between tap and tap old. It's important that this executes after the condition so that we actually have a value for the latter. Finally, let's connect it to this bit to update the variable. Next, let's update the current position using a vector lerp with p as the start, pg as the end, and 0.25 as the amount. Then, we carry those changes to the player's position. In repass play, we can now move the player. However, if we drag far enough, the ship goes out of bounds, nowhere to be seen. Thus, it's imperative to establish the playfield so that our player doesn't get out. Firstly, we'll save the camera distance to a variable as we would need this in determining the edges. Utilize the block size 2D to get the screen width and height in blocks, and add in the variables to keep track of the bounds. From here, we'll divide our size by 2, as we'll be branching out from the origin point, which is at the middle, therefore adding or subtracting with these values should get us to the edges. So let's go ahead and set our variables. Afterwards, let's go back to our code and amend our player movement. Split the vector up into separate coordinates, clamp these values using our min and max variables to keep our play within the screen, and compile them back into a vector. When we test this, the player is now fully contained within the confines of our playfield. The next thing in our list is to take care of the particles. We want them to spawn somewhere along the bottom of the ship and have them move outwards. After a certain point, they disappear. The first thing we'll do is attach an if condition at the very start of this chain of code. So when we want to stop the game, we just set this variable to true and everything should be disabled. And for this next part, we'll be using a random block. I suppose you are already familiar with its function, but essentially in every frame it generates a random number between your minimum and maximum inputs. If these inputs are left untouched, then that value goes between 0 and 1. Keep in mind that this outputs a float. If you want a whole number, then you would need to round that value. Take note of the fact that it creates a new number every frame. That way, we can create a system that can randomly execute by comparing its value and checking if it's greater than a certain value. In my case, I've set it to 0.5 to have a 50% chance of spawning a particle. Naturally, the next step is to create a copy of the particle and save it into a list. However, since we'll be trying to spawn an object every frame, this leaves us with a lot of items. And although they get deleted at a certain point, we'll still be left with a pretty huge list riddled with empty spaces. So what do we do? Let me visually demonstrate a fix to this problem. Whenever we try to spawn an object, we'll first look through the list and see if there are any open spots. At the start, there won't be any because there's no list. So we'll append this object and update the list length. At the second try, since the first item still holds an object, we do the same thing. Insert it at the end and update. At the third try, same thing, first two items are occupied, you know the drill. But let's say the first particle has run its course and gets removed. Now, when we spawn an object, instead of bringing it to the end, we can simply take the place of the first spot as it is currently empty. That is essentially the logic behind the system. Loop through the list, override items if available, and append if necessary. That way, we won't have a list length that is ever increasing, as after a while, all of the created particles will be continually sorted in the same boxes and therefore that value stagnates. Let's build a loop by setting the index number to 0 and checking if it's less than the list length, in this case pslen. If this is true, which it would be if the list actually has an item, then we check for that specific item to see if it exists. If it's false, then that means this spot isn't empty, so we increment the index and go back. If it's true, however, then we save the index to a variable and stop the loop. If the index is greater than the length, then that means that there aren't any spots, so we save the list length into a variable and increase it. Next, let's create a copy of the particle and save it into a list with I as the index. Let's also lock its position and rotation since it's a physical block and we want it to be static. Then we update its position. We'll use P as the starting point and from here, add an offset with random x and z values. We'll also adjust that offset a little bit so that it shows up at the bottom of the ship. You can also play around with the values until you have something that works. Now, it creates the particles, but they all have the same color. Remember the reason why we have 4 colors in our particles? What we'll do is create a rotation, then have a random number between 0 to 4, floor it to get an integer between 0 and 3, and multiply it by 90. That way, we get to show one of the 4 faces. Let's also randomize the y value between 0 and 360. When we press play, the ship now spews out rotated particles of varying colors. Next, let's add a property that determines the lifetime of the particle and have it be between 30 to 50 frames. Then, let's create a loop away from the main code so that it wouldn't be affected by our if condition. Save the index to a variable and check if the list item isn't empty. If it isn't, then we update the particle's position to move downwards. We'll also add an if condition that checks if PST is less than 0. If this returns false, then we decrease its value. Once it is below 0, then we delete the object. Now, the particles slide downwards and despawn after a short while. And if we quickly inspect the list length, notice how it is not always increasing. The next thing we'll spawn is the bullet. Unlike the particles earlier, they will spawn within a fixed interval. We can achieve this by taking the current frame block, have a modulo of 5 so it goes between 0 to 4, and checking if it's equal to 0, making it execute once every 5 frames. Now, we'll also be applying the same system we did with finding the open spaces in the list, but instead of duplicating our work, I think it's best to create a custom script block so that we could easily reuse it and tweak it if needed. We'll need 3 inputs and 3 outputs. The before and after wires to connect it to our code, the object list variable, the list length, and execute wire once the system finds an empty item, and that item's index. Remember that our input wires are always at the top or to the right, while the output wires are at the bottom or to the left. The plug wire should also be 3 voxels away from the edge and 1 voxel away from the bottom, to have them quickly snap to our variables and values. For the index, we'll just take I and bring it outside the block. Once done, we can simply replace all of this code with our script block, attaching our variables to their respective inputs. As you can see, everything still works fine. Let's find an open spot for the bullet list, spawn in the object, and assign it to the list using the found index. We'll lock the position and rotation, and place it to appear in front of the player. When we test this, the game now spawns the bullets in a fixed rate, but we still have to move them. Add another loop, this time for the bullets, wherein we'll do the same thing we did earlier with only running the code if the object is in the level. From here, we can update the bullet's position to glide upwards. And up they go. Then we have to check if the bullet has gone out of bounds. We do this by getting its Z position and checking if it's greater than maximum Z value, which if you remember is the top edge of the screen. If that's the case, then we delete the object as well as add an SFX for testing purposes. Now if the bullet is outside the area, then we hear a sound as it gets removed. We now have to spawn in the obstacles that are randomly placed on top of the screen as they scoot downwards. Similar to the bullets, we'll spawn them within a fixed interval, in this case once every 15 frames. Then let's find an open item, clone the obstacle model, and store it in the list via our given index. Then we have to set its position. We'll create a vector wherein the x position ranges between our minimum and maximum x values, the y position is 0.5, and the z position is max z plus 1, giving us a random position somewhere along the top of the screen. Let's also add in a property that determines the health of the obstacle and set it to 5. Now we'll attach a loop for the obstacles in the main loop since we would want them to stop moving if the game is over. Again, only run the next bit of code if the object actually exists. Instead of directly adding in a vector to offset the obstacles, I will actually save it to a variable as I would want to increase the velocity as the player progresses. Then, update the position by subtracting it with a variable. Now, the boxes are coming down from the void up above. Next, let's check if the obstacle's Z position is less than the minimum value. If it is, then that means it's off the screen and therefore should be erased. Bring in an SFX to debug, check if it works, and as expected, we hear a noise if one of those cells disappear. Now that we have our obstacles, our player ship has something to bump to. Therefore, we have to set up its collision. However, this part will only be truly applicable if you also have a triangle model like mine. What will essentially happen is we'll implement a loop that runs 3 times to cover the left side, the middle, and the right side. We'll project raycasts that start from the bottom of the ship and have them coalesce in the middle once they reach the top. We'll also do this vice versa to check both ways. A is the point at the bottom of the player, while B is at the top. We'll use P as the starting point in both cases and stem from there. For the X position, let's subtract the index by 1 to get a negative number, 0, or a positive number. We then multiply it with a value. The greater the magnitude is, the farther it is from the ship. Set negative 0.25 as the Y value, and for the Z coordinate, have negative 0.5 at A and 0.5 at B, so we can go from the bottom to the top. Finally, we can use these variables as the points of our raycast, for which we'll have 2 of them so we can look for both sides. Let's use the OR block to combine these 2 conditions as we want to do something as long as any of them hits an object. If it does, we simply set the stop variable to true. When we press play, as soon as we hit an obstacle, the game stops. Let's also attach some threading sound effects. And add force block and play around with the values. And trigger the loose block. Now the player spins around and fades into non-existence if it ever hits an obstacle. Next, let's also cast some rays to our bullets. We would want to create 2 diagonals to roughly cover its area. We'll use the object's position as the starting point and add an offset. For the X position, let's take the index and subtract by 0.5 to have a negative and positive counterparts before multiplying by 0.25. For the B variable, negate this value. That way, the first line goes from left to right, and the second goes from right to left. For the Z position, start with an offset of negative 0.25, and end with 0.25 to go back to front. Then, apply it to the raycast. If this first condition is true, then get the detected object. Otherwise, run the second raycast. If this is true, then do the same. Once we have our object, then we should loop through all of the obstacles and search for its corresponding box. What we have here is a combination of 2 conditions. One that checks if this object matches with what we've detected from the raycast, and the other for checking if that object actually exists. Though in hindsight that's pretty unnecessary since this will only run if the raycast has actually hit something, that being an object within the game. If this is the box that we're looking for, then we set a boolean property to true that tells the game that this box has been hit. Then we decrease its HP. Check if it's greater than 0, though we'll come back to this later. Destroy the bullet and then hit SFX. Now, the bullet gets removed once it comes in contact with a box. Going back to our loop for the obstacles, we'll be flipping its rotation if the box has been hit. We'll start with a default rotation of 0, an if condition that checks for this boolean, and if this is true, set it back to false and set the X value to 180. This makes the box appear white for 1 frame whenever they get damaged. If the obstacle's HP is less than or equal to 0, then we increase the score by 10. In the original game, a visual indicator also pops up whenever the player successfully destroys the square. So let's initialize our indicator here and make it static. Once the box gets deleted, let's show the pop-up, set its lifetime to 30 frames, and set its current and goal position based on our vector variable. Though let's increase the height to have it appear on top and add an offset of 1 to our goal so that it floats slightly upward. Then let's check if UI time is greater than 0. If it is, then we decrease it. This determines how long the pop-up lasts before it disappears. You know what, we can actually move this bit over here since its visibility is completely dependent if this variable has a value. Let's update the UI position via a lerp before updating the object's position. Now it seems to work, but the bullet shouldn't destroy the boxes in one hit. Well, turns out this was connected to the true output. And as you can see, everything is working really well. Let's also add in a way to display the score. The game is almost complete. All we have to worry about is making the game harder as the play progresses. First of all, let's increase the obstacle's velocity. Make a vector, have the initial speed be 0.05, and add a value based on the score. Let's divide it by 10 and multiply by 0.01. That way, every time the player scores, this increases by 0.01. And if we check if this works, you can notice that it slowly ramps up as we destroy the squares. However, the spawn rate can't quite catch up if the boxes are moving quickly. Thus, we also have to make some changes in that area. Take the score, divide by 30, floor, and get the minimum value between this and 10, before subtracting it to 15. The reason why we wanted to floor it is so that we can have a whole number. Since we're using a modulo and the frame block outputs an integer, the other input should also be an integer so that this can actually run once every X amount of frames. Then we have 10 as the maximum value, because we don't want the game to essentially spawn an obstacle every frame at some point. And if we quickly test this, you can see that it spawns more obstacles as the velocity increases. This final part is completely optional, but if we head out of the game and take a look at the thumbnail, yeah, it's not looking good. At the end of the score loop, let's attach a box art sensor. What this block does is it executes code whenever the game is creating a thumbnail for the game. This block will not run at any point during the gameplay, but only once when the game is generating the screenshot to display at the game's disk. From here, we attach another camera block. It is incredibly crucial to have this run after the main camera to override the view. If it isn't, then this won't work at all. Let's use the player's position as the camera position, mess around with the rotation, and set the distance close. I'll also go to where we spawn the particles and make sure that this doesn't run during the first frame. Say that the particle shows up at the first frame. Notice how you can see it in the box art. That's why we have to do this part. Also, if you play the game, you can still see the raycast. That's because there aren't any actual blocks in the level apart from the script container. All we have to do is to place another block and that should do the trick. We have successfully accomplished our goal of recreating this game. I hope you learned something by following this tutorial. As always, there is a GitHub link below that takes you to the code screenshots, so if you ever need to compare your work and see what went wrong, then that's the place to go. Thank you for watching, and I'll see you at the next one.